Welcome. This screencast is going to look at the last part of Section 3 and Chapter 5 of the Brown SL Chemistry book, where they talk about ozone's role in our atmosphere in helping to screen out the harmful UV radiation that is part of sun's emission spectra. So Earth is unique in that it has an atmosphere rich in oxygen, which is why we're a planet with life on it. And oxygen is present around us in two forms: oxygen gas, or normal oxygen that you think about that we need to live, and then ozone. And down in the area of the atmosphere where we hang out, ozone is considered a pollutant. That's not a good thing. But up in the stratosphere, there's a lot of ozone, and combined with oxygen gas, it helps protect us from the sun's harmful rays. So what you need to know about O2 and O3 is that oxygen gas contains one double bond between the two oxygen atoms. So I'll just draw this in here quickly. Whereas ozone contains one double and one single bond, since it's got three oxygen, so there's resonance. So we talk about the ozone bond being really a 1.5 order because its bond length and strength is some kind of hybrid between 1 and 2, whereas oxygen actually has the stronger, shorter bond with an order of 2 or a double bond. So the weaker bond in ozone means it's broken more easily by the high frequency, high energy radiation that hits it. And that's a good thing because that's its function up in the stratosphere, is to absorb these high frequency waves and prevent them from reaching us down here on planet Earth. So both forms of oxygen can be broken down by UV radiation, but the ozone is broken down more easily by UV radiation. So knowing that the bond enthalpy for O3 is 363 kilojoules per mole, we can calculate the wavelength or frequency of light needed to break this. So if we have a little bit of a throwback here, remember energy is equal to Planck's constant times frequency, or if we sub in wavelength, it would be equal to Planck's constant times the speed of light over the wavelength. So if I know it's 363 kilojoules per mole, I can go ahead and plug in Planck's constant, 6.636 times 10 to minus 34th, and that's joule seconds. I'm sure you all remember that. And then I can solve for the frequency, and I come up with the frequency equal to 5.47 times 10 to the 35th, and that's per seconds or hertz, whatever you want to call it. And that would be the frequency. And I could do the same thing to find the wavelength, or I could just use C equals wavelength times frequency. And I know that speed of light is 3 times 10 to the 8th. I've got my frequency, 5.47 times 10 to the 35th. I can solve for wavelength. So if I solve for this is a wavelength equal to 5.48 times 10 to the minus 28th. And not a surprise that we're talking about very short, very high frequency waves. That's why they're so dangerous for us, and we need ozone to filter them out. So how exactly does this happen? Well, you maybe know that as you travel up in the atmosphere, it gets cooler. But what you didn't know is if you keep going up around 12 kilometers, it suddenly warms up. And this is due to something called the Chapman Cycle, or this is really what we think of as the ozone cycle. This is where the ozone is at, and it's working, it's performing its job to keep us safe down below here. So this little picture here is what's known as the Chapman Cycle. And what happens is, in step 1, you have a photon, actually before step 1 here, you have a photon of ultraviolet C, that's the really dangerous stuff, that hits an O2 molecule. And in step 1, that O2 molecule gets split into 2 oxygen atoms. Now remember, if you're absorbing energy, that makes it an endothermic process right here. So this absorbs energy. Well, these 2 oxygen atoms, what they don't show you is these are actually free radicals. It's got a little electron there, an unpaired electron. Actually, we could more accurately show it with 2. But free radicals are when you have things like oxygen atoms or halogen atoms. When they're not bonded, they're extremely reactive. And that's what a free radical is, if you've heard that term before. And because they're so reactive, they're going to bond with the first thing available. So when you have free radicals in the atmosphere around you or free radicals in your body, That's when bad things can happen, is because they're so reactive and they're just going to latch on to whatever they can. And sometimes that's not things you want them latching onto. But so when you have these two oxygen atoms, they're fairly easily going to hook up with O2 molecule, an oxygen atom. And in step 2 now, this will be exothermic. They will release some energy as they form the ozone molecule. Okay, so the ozone is formed in the stratosphere through an exothermic process. But then the O3 is also going to absorb UVB, which is also dangerous to us. And when that happens, then the O3 breaks back down. So when it absorbs O3, when O3 absorbs UVB, it goes this way and it breaks it back down into O2 and a free radical. Let me just put the little dot there to show it's a free radical. I have a little trouble with my dots. Or some of the O3 doesn't absorb UVB, and it can go on to form new oxygen molecules in step 4. Now, this is a much slower process. These first 3 are the ones that happen far more frequently, with step 3 also being an endothermic step, and then step 4 is also an exothermic step. So the 2 endothermic steps are absorbing the dangerous radiation, and UVC is the higher frequency, which is why it can break the O2 bond. UVB is slightly less frequency, slightly less energy, but they're both dangerous to us. But then we also have 2 exothermic steps, which is why the atmosphere actually gets slightly warmer there, is because of these exothermic steps. All said, ozone is naturally around 10 parts per million. It should form and deplete at a constant rate if we're not adding any more crap into our atmosphere to disrupt this cycle, and it's known as a steady state. Back in the 70s and before that, but especially in the 70s as air conditioning and refrigerants and stuff were popular and aerosols became popular, we were using a chemical called CFCs, chlorofluorocarbons, to propel the aerosols and to run our air conditioners. And what we didn't know is those CFCs were traveling up into the upper atmosphere, and they were disrupting the natural Chapman cycle. In fact, it's estimated one CFC molecule can destroy 1,000 ozone molecules. So that's definitely disrupting the cycle. And when you remember there's only 10 parts per million, you take 1,000 out, you've disrupted a big chunk of the ozone. So with the decrease in the ozone above us, that means there's going to be increased exposure to higher energy UVB and UVC radiation, which is dangerous because they produce the free radicals, which are linked to cancer. Even if it's, if we're putting on our sunscreen and being protective, it's still going to damage our crops. So definitely a bad thing. The good news is that since the early 90s or late 80s, CFCs have been phased out in most countries. And so we're seeing the ozone repair itself now that we figured out what we were doing to damage it.